How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
Imagine you are holding a long, thin strip of paper. On this paper, written in a single line, is a sequence of letters. This is a recipe, but it is not a recipe for a cake or a casserole. It is a recipe for a machine that breathes, a machine that fights off viruses, a machine that digests your lunch. Now, imagine that to build this machine, you do not need a screwdriver or a wrench. You simply let go of the paper strip. Instantly, faster than the blink of an eye, that paper crumples, twists, and knots itself into a perfect, intricate, three-dimensional shape. It becomes a tiny origami robot, and just because of that specific shape, it starts to work. This sounds like magic. It sounds like something from a science fiction novel about programmable matter. But this is exactly what is happening inside every single cell of your body, right now, billions of times a second. This is the phenomenon of protein folding. It is the fundamental manufacturing process of life. For half a century, we knew the letters on the paper. We could read the DNA, but we had no idea how those letters turned into the shape. We were staring at the instruction manual, but we could not see the machine. It was biology's greatest black box. Then, a computer program showed up. It didn't just guess the shape. It solved the puzzle. But how does a collection of silicon chips understand the geometry of life better than human physicists? What simple rules allow an artificial intelligence to see the invisible structures of our biology? Today, we are going to talk about AlphaFold, the protein folding problem, and the geometry of life. Welcome to First Principles. To understand why AlphaFold is such a seismic shift, we first have to understand the magic we see in the biological world. We often think of biology as wet and squishy. We think of tissues, organs, and fluids. But if you zoom in, way past the cell level, down to the molecular level, biology is actually engineering. It is mechanical. Your body is made of proteins. But forget the word protein for a second. Think of them as nanobots. You have a nanobot called hemoglobin that is shaped like a catcher's mitt, designed perfectly to hold 4 molecules of oxygen and ferry them through your blood. You have nanobots called enzymes that are shaped like Pac-Man, chewing up food to release energy. You have antibodies shaped like Ys that act as clamps, locking onto invaders so the immune system can destroy them. Everything these machines do depends entirely on their shape. If the hemoglobin is bent the wrong way, you get sickle cell anemia. If the insulin receptor is shaped incorrectly, you get diabetes. In the world of proteins, structure is function. If you break the shape, you break the machine. For decades, this has been the bottleneck of modern medicine. We are incredible at reading the genetic code. We can sequence a human genome in a day for a few $100s. We have giant databases filled with hundreds of millions of gene sequences. These are the recipes. But having the recipe does not mean you know what the cake looks like. This is the gap. We have the 1D information, the string of letters. We are desperate for the 3D information, the shape of the machine. Without the shape, we are shooting in the dark. Designing a drug without knowing the shape of the protein it is supposed to target is like trying to make a key for a lock you have never seen. This brings us to the pioneers and the problem that haunted them. The story really begins in the 1950s and 60s. Scientists knew that proteins were made of long chains of amino acids. There are 20 different types of amino acids, and they are strung together like beads on a necklace. In 1972, a chemist named Christian Anfinsen made a bold claim. He won a Nobel Prize for it. He stated that the 3D structure of a protein is determined entirely by its 1D sequence of amino acids. In other words, the beads themselves contain all the instructions needed to fold the necklace into a specific knot. You don't need an external mold or a machine to shape it. The information is intrinsic. This was a massive discovery, but it came with a terrifying mathematical headache. It became known as Levinthal's paradox. Cyrus Levinthal, a molecular biologist, did the math. He looked at a simple protein chain and calculated how many possible ways it could fold. Proteins are flexible. Each link in the chain can rotate. If you have a chain with just 100 beads, the number of possible configurations is astronomical. The number Levinthal came up with was 10 to the power of 300. That number is impossible to visualize. For context, the number of atoms in the entire observable universe is roughly 10 to the power of 80. 10 to the 300 is effectively infinity. Levinthal pointed out that if a protein had to randomly try every possible shape to find the right one, even if it tried 1 trillion shapes a second, it would take longer than the age of the universe to finish folding. Yet, in your body, proteins fold into their perfect, native shape in milliseconds. This paradox broke the brains of physicists. How does nature find the needle in a haystack the size of the universe, instantly, every single time? For 50 years, humans tried to solve this the hard way. We used experimental physics. The gold standard is a technique called X-ray crystallography. You take a protein, you purify it, you concentrate it until it forms a crystal, which is incredibly difficult to do, and then you blast it with high-powered X-rays. By looking at how the X-rays bounce off, you can mathematically reconstruct the 3D shape. It is slow. It is painful. A single structure can take a PhD student 4 years to solve. It costs tens of thousands of dollars per structure, while we have hundreds of millions of gene sequences. Until recently, we had only mapped the 3D structures of about 170,000 proteins. We were drowning in data, but starving for knowledge. Then came CASP, the critical assessment of structure prediction. It is the Olympics of protein folding. Every 2 years, organizers release a list of protein sequences whose structures have been solved by experiments but not yet published. Teams from around the world try to predict the shapes using computers. For decades, the progress was incremental. Computers were bad at it. They would get the general blob right, but the fine details, the precise location of the atoms, were usually wrong. In this competition, success is measured by a score called GDT. Basically, a score of 0 is a mess, and a score of 100 is a perfect match to the experimental data. For years, the winning teams hovered around scores of 40 or 50. It was assumed that solving the problem computationally was decades away. Then came 2018. A team from DeepMind, the artificial intelligence lab owned by Google, entered the competition with a system called AlphaFold. They didn't just win, they crushed everyone. But it was in 2020, with AlphaFold 2, that the world truly changed. They achieved a median score of 92.4. In the world of science, 90 is considered indistinguishable from experimental methods. They had effectively solved the problem. The organizers of the competition, hardened skeptics who had seen decades of failure, were stunned. One of them famously said, "This changes everything." But how? How did a neural network solve a physics problem that stumped humans for half a century? Did it simulate the physics? Did it learn the laws of thermodynamics? No, and this is where we need to open the black box. There is a common misconception that AlphaFold works by simulating the folding process. We assume it acts like a physics engine in a video game, calculating the forces between every atom, watching them push and pull until the protein settles into its shape. This is called molecular dynamics, and people do this. But it is computationally incredibly expensive. It is too slow to solve the big problem. AlphaFold does not watch the movie of the folding. It skips to the ending. It looks at the sequence and predicts the final structure directly. To understand how, let's establish our core analogy. We are going back to the bead necklace. Imagine you have a necklace with 100 beads. Some beads are magnetic, some are covered in Velcro, some are made of rubber, some are positively charged, some are negative. If you lay this necklace out in a straight line, you have the sequence. Bead 1 is magnetic, bead 2 is rubber, bead 3 is Velcro. Now imagine you want to know which beads will end up touching each other when the necklace crumples up. In the straight line, bead number 1 is very far away from bead number 50. But if the necklace folds in half, bead 1 and bead 50 might snap together. This is the key insight. The 3D structure of a protein can be represented as a map of contacts. If you know that bead 1 touches bead 50, and bead 5 touches bead 20, and bead 10 touches bead 12, you can constrain the shape. You are creating a roadmap of the folded state. This is what AlphaFold is looking for. It is not trying to place atoms in 3D space immediately. It is trying to predict a distance map. Think of a distance map like a grid. On the horizontal axis, you list all the amino acids in order. On the vertical axis, you list them all again. Every square on the grid represents the intersection of two amino acids. If they are close together in the 3D structure, you color the square dark. If they are far apart, you leave it light. If you look at the distance map of a folded protein, it looks like a beautiful, complex pattern of islands and diagonals. AlphaFold treats this like an image recognition problem. In the early days of deep learning, we got really good at recognizing cats in photos. A neural network looks for patterns of pixels. An ear is a triangle shape here. A whisker is a line there. AlphaFold 1 took the sequence of amino acids and tried to predict this image, this distance map. It said, I've seen thousands of proteins before. When I see a pattern of amino acids like alanine, glycine, cysteine, it usually results in a contact map that looks like this. It was a brilliant application of computer vision to biology. But it wasn't enough. It was good, but not great. To get to 90% accuracy, DeepMind had to go back to first principles. They had to stop treating the protein like an image and start treating it like what it actually is, a graph in 3D space. This brings us to the real innovation, geometric deep learning. An image is a grid of pixels. It is flat, it is rigid, but a protein is a cloud of points floating in space. It has geometry. One of the fundamental rules of physics is something called invariance. If I hand you a coffee cup and you turn it upside down or spin it around, it is still a coffee cup. Its internal structure hasn't changed. The distance between the handle and the rim is the same, no matter how you hold it. Traditional neural networks struggle with this. If you show a standard AI a picture of a cat upside down, it might not know it's a cat. You have to train it on thousands of upside-down cats for it to learn. AlphaFold 2 was built with this physical intuition baked in. It uses a type of neural network architecture called a transformer, the same technology behind large language models like ChatGPT, but modified for geometry. In a language model, the attention mechanism allows the AI to understand the relationship between words. In the sentence, "The animal didn't cross the street because it was too tired," the AI uses attention to figure out that the word "it" refers to the animal and not the street. AlphaFold uses this same attention mechanism to reason about the beads on the necklace. It asks, which other amino acids should I be paying attention to? But here is the brilliance. It doesn't just look at the sequence. It builds a floating, abstract 3D model in its mind and constantly updates it. The system works in 2 tracks, running parallel. Track 1 handles the information about the sequence, the list of ingredients. Track 2 handles the information about the geometry, where the beads are in space relative to each other. These 2 tracks talk to each other constantly. The sequence track says, "Hey, I see a positive charge here and a negative charge there." The geometry track replies, "Okay, I'll pull those 2 points closer together in the 3D model." Then the geometry track might say, "Wait, if I pull these closer, this other loop has to swing out of the way because 2 atoms can't occupy the same space." It passes that info back to the sequence track. They go back and forth, refining the model, iterating, spiraling closer and closer to the truth. This architecture is called the evoformer. It is trying to satisfy the physical constraints of the molecule while matching the patterns it learned from the data. This sounds incredibly sophisticated, and it is. It is one of the most complex AI systems ever built. But even with all this geometric reasoning, there is a missing piece. If you just gave AlphaFold a single sequence of a protein from a human, it might still struggle. The physics is just too complex to predict from scratch every time. AlphaFold cheats, or rather, it uses a lifeline that nature has left for us. This is the unseen giant. This is the aha moment where the technology connects with the deep history of life on Earth. The secret weapon of AlphaFold is not just geometry, it is evolution. This is the principle of multiple sequence alignment, or MSA. Here is the concept. Evolution is a ruthless editor. If a protein is important for life, its structure is conserved. The shape must stay the same or the organism dies. However, the sequence, the letters, can drift a little bit. Over millions of years, random mutations happen. Maybe an A turns into a G. As long as that change doesn't break the shape of the protein, the organism survives. Now imagine 2 amino acids. Let's call them bead X and bead Y in the 3D folded structure. They are touching each other. They are locked together like a key in a keyhole. Maybe bead X is positively charged and bead Y is negatively charged. They stick. If a mutation happens and bead X becomes neutral, the magnetic stickiness is gone. The protein falls apart. The organism dies. That mutation is lost to history. But suppose a miracle happens. At the exact same time bead X mutates, bead Y also mutates to become compatible with the new bead X. They change together. They co-evolve. Because they both changed in a way that preserves the connection, the protein shape stays the same and the organism lives. This is the smoking gun. If you look at the DNA of a human, a mouse, a cow, and a fish, and you line up the gene for the same protein, you will see differences. But if you see that every time column 10 changes, column 50 changes with it, you know something profound. You know that column 10 and column 50 are physically connected in the 3D structure. They are dancing partners. This is what AlphaFold does before it even starts folding. It scours the databases of genetic sequences from all over the tree of life. It builds a massive spreadsheet comparing the protein across thousands of species. It looks for these correlations. It looks for the coevolutionary signals. It effectively uses the last 3.5 billion years of evolutionary experiments to cheat on the physics test. It doesn't need to calculate the exact energy of the bond between X and Y, because evolution has already proven that X and Y must be touching. This is the synthesis. AlphaFold combines the hard logic of geometry, the evoformer, with the deep time of evolutionary history, the MSA. It uses the wisdom of the ancients, the evolutionary record, to inform the intuition of the machine, the neural network. So, what happens when you turn this on? The impact is hard to overstate. In 2022, DeepMind released the predicted structures for nearly all known proteins, 200 million structures. They put it online for free. Overnight, the number of known protein structures jumped from 170,000 to 200 million. We went from mapping a small neighborhood to mapping the entire planet. Biologists who had been stuck on a single protein for a decade, waiting for crystals to grow, suddenly had a high-accuracy model on their laptop in minutes. We are seeing the acceleration of drug discovery. If a bacteria has a protein that allows it to resist antibiotics, we can now see the shape of that protein instantly. We can design molecules to jam it. We are seeing it in climate science. Scientists are trying to engineer enzymes that eat plastic. To do that, they need to tweak the structure of existing enzymes. AlphaFold allows them to simulate those changes rapidly. But beyond the utility, there is a philosophical shift here. For a long time, we treated biology as a special, messy science. It was distinct from the clean, axiomatic worlds of physics and math. Biology was full of exceptions and noise. AlphaFold proves that biology is, at its core, an information problem. It proves that the complexity of life is not magic, it is geometry, it is computable. We often fear that AI will replace human creativity or human understanding, but in this case, AI acted as a telescope. The telescope didn't make the stars, it allowed us to see them. AlphaFold didn't invent the biology, it allowed us to finally read the manual that has been written inside us since the beginning of life. We started with a string of letters and a paradox. We ended with a three-dimensional machine and a revolution. The lesson of AlphaFold is that the complex, chaotic dance of life follows simple, elegant rules. And if we listen close enough to the whispers of evolution and apply the lens of geometry, we can finally see the shape of things to come. The protein folding problem was once called a grand challenge. Now it is a tool, and just like the microscope or the telescope before it, the real excitement isn't about the tool itself, it's about what we are going to discover now that we can finally see.
You've been listening to First Principles. Until next time, stay curious.